Hello my students, your physics teacher Hassan Darwish with you, and with the explanation of chapter 5. In video 1 I explained objective 1, you remember, the definition of a nuclear reaction and its difference from the radioactivity. In this video I am going to explain the second objective, distinguish between two types of stimulated nuclear reaction, fission and fusion. So in this video we are going to focus on fission reaction, and the next video I will explain fusion reaction. Let's start. You remember in video 1, a nuclear reaction occurs when a nucleus is bombarded by a particle so that it changes into new nucleus or nuclei. Let's study this special nuclear reaction called nuclear fission. First, let's see the video. In this video, we have, look here, you see, we have uranium nucleus here, or heavy nucleus, bombarded by a particle. Look what happened to this nucleus. Explodes, means make fission, and divides into two smaller nuclei, which are called fission fragment. Clear? With liberation of 3 neutrons. Okay? Let me repeat it. So we have here a neutron and we have here a nucleus. Look, neutron and a nucleus. We bombard this heavy nucleus, usually uranium-235. We bombard it by the neutron. Now, fission means splits into 2 smaller nuclei with liberation of 3 neutrons. We could have liberation of 1 neutron or 2 neutrons, not always 3 neutrons. Okay? That's the meaning of nuclear fission reaction. So fission reaction, here is the heavy nucleus, uranium-235, bombarded by this slow neutron. What happened to this nucleus? Splits, see, divides or splits into 2 smaller nuclei. We call them fission fragments. And liberation of neutrons. Here we have 2 neutrons. We could have 3. We could have 5. We could have 1 neutron. But what is important in this reaction is the energy liberated. E liberated, delta mc squared, around 200 mega electron volt. Very huge amount of energy liberated. Okay? So we keep in mind means we learn by heart the definition. By heart. Okay? So is a stimulated reaction during which heavy nucleus is divided into 2 lighter nuclei under the impact of a slow, means thermal neutron. Be careful. This is the condition of thermal of nuclear fission. When he asks us about the condition, we say thermal neutron or slow neutron means kinetic energy less than 0.1 electron volt, EV electron volt. Okay? Any problem? Now example on this fission reaction. Look, here we have 2 examples. Uranium nucleus bombarded by the neutron as in the video. divides into two smaller nuclei, lighter nuclei, with liberation here 2 neutron. Another example, 235 uranium-2 is bombarded by a slow neutron, divides into two lighter nuclei, krypton and barium. But here liberation of 3 neutron. We don't know what if the reaction will liberate 2 neutron or 3 neutron. But what is important for us, the mass number must be conserved, the atomic number must be conserved. Means if you add 1 plus 235, you get 236. So here 94 plus 140 plus 2, you get 236. And atomic number conserved, 0 plus 92, 92. 38 plus 54 plus 0, you get 92. Clear? Okay. Now, the energy liberated by one fission reaction, E equal delta mc squared, is about 200 mega electron volt, which is very, very huge amount of energy. Now, this reaction is used at the beginning of the Second World War to invent what we call atomic bomb. Okay, let's see how. In order to produce the atomic bomb, you must have something called a chain reaction. What is a chain reaction? Is a successive multiplication of fission reaction. Means here the 2 neutron will trigger 2 fission reaction, a new fission reaction. Here 3 neutron will trigger new 3 fission reaction. Means in this reaction you have 200 MeV, mega electron volt. Now when 3 reaction occur, you have 600 mega electron volt. Let's see how. Here we have the new uranium bombarded by the thermal neutron, then divided into krypton and barium with liberation of 3 neutron. Now each neutron trigger a new fission. So here we have 1 fission, here we have 3 fission. Clear? So here you have 200 mega electron volt. Now you get here 600, 200, 200, 200, 600 mega electron volt, and the reaction continues in an uncontrollable fashion. This is called the chain reaction. Let's see in the video what happened during chain reaction if it is uncontrolled. Here, look, you have uranium nucleus splits under the impact of 1 neutron into 2 lighter nuclei with liberation of 2 neutron. Look what happens. You see multiplication of fission reaction. That's the atomic bomb. That's what happened. In fact, this is the energy liberated by chain reaction if it is uncontrolled reaction. Okay? Now let's solve an application in this video also about fission reaction. Example. In this example, we have this reaction. Okay? Uranium bombarded by neutron. Determine X and Y. Here is X and here is Y. Of course, apply what? Conservation of mass number and atomic number. So, sorry. So here, conservation of part A. conservation of mass number, you get 1 plus 235 equals 91 plus 142 plus x into 1, of course, because mass number of neutrons 1, plus y into 0. And then you get, if you do the calculation, x equal 3. Okay? Similarly, conservation of atomic number, also you get 0 plus 92 equals 40 plus 58, okay, plus x into 0, 0, plus y into minus 1 is minus y, okay? If you go back here, y, x times 0, 0, y times minus 1, minus y, okay? If you do the calculation, then you get y equal 6. Okay, any problem? Part B. We want to determine the mass defect. Mass defect means delta M. Delta M equal mass before reaction minus mass after the reaction. Before reaction here we have neutron and uranium. After reaction we have zirconium, cerium, neutron plus electron. He says neglect the mass of the electron. Means mass of an electron 0. Okay? So if you add them and you do the calculation, then you get 0.2128. But what's the unit here? The unit is U. Okay, because the units are given here in U. Now we change into kilogram times to change it from U into kilogram. You multiply by this number. Multiply by this number, you get 3.53 times 10 to the minus 28 kilogram. Now we need the energy liberated by the reaction. Energy liberated, you know, it is equal, part C, equal delta MC squared, okay? So energy liberated equal delta M C squared. If you do the calculation, you get 3.2 times 10 to the minus 11 joules. Sorry. 11 joules. Now, the question is, can this reaction lead to a chain reaction as we see in the video? Why? Yes, it can. Why? Because this reaction liberates more than 1 neutron. It liberates 3 neutrons. Clear? So yes, it leads to a fission reaction. That's enough in this video. See you in the next video with the explanation of the fusion reaction. Take care. Bye-bye.